So, staying with tangents and slopes and equations, find the coordinates of the point on the curve y equals x squared plus 2x plus 1, at which the slope of the tangent to the curve is 4. So that means straight away dy dx is equal to 4. What is dy dx with respect to the function? It's 2 by x plus 2. So 2x plus 2 must be equal to 4, and that implies that 2x is equal to 4 minus 2 is 2, x is equal to 1. So now that we know that x is equal to 1, we want to find the corresponding y value because we're looking for the coordinates. So we sub x equals to 1 into the original function, and we get y equals 4. So the point 1, comma 4 is on the curve, and it's on the curve 1, comma 4. So wherever that is, sorry, let's go like that, something like that. 1, 4, and 1, 4, and there's a tangent there. The slope of that tangent is 4. We found the point. Okay. Another example, find the coordinates of the point on the curve y equals x squared minus 3x plus 7, at which the tangent of the curve is parallel to the line y equals 3x plus 4. Well, if the tangent is parallel to this line, then the slope of the tangent is same as the slope of the line, which is here, is 3. So we just need to know how to pick that piece of information out there. Okay. So the curve is x squared minus 3x plus 7, so do y dx, okay, the slope of the tangent at a point on the curve is equal to 2x minus 3, and now the point where the slope is equal to 3, so 2x minus 3 is equal to 3, that means x is equal to 3. So the x coordinate of the point where that tangent kisses that curve is 3. So when x is equal to 3, we'll plug that back in to find the y coordinate, y equals 7. So the point on the curve is 3, 7. So in summary, there's a curve, there's a tangent, the tangent hits the curve, or kisses or touches the curve at 3, 7, and its slope is 3. Now, question 6 in the book gives a parabola derived from x squared minus 2x minus 3. If f dash x dy dx at point P is 2, find its coordinate. Okay, so f of x is x squared so that means, what does that mean? That means the slope of the tangent here is 2, okay, at that point P. So find its coordinate. X squared minus 2x minus 3 is the function. So f dash x is equal to 2x minus 2. That is equal to 2. So x is equal to 2. And if x is equal to 2, then y must be equal to, we'll plug 2 into where we see x in the function, y must be equal to minus 3. So P must be at the point 2, minus 3. Let's look at question 15 on page 520, text and tests. If the slope of the tangent to the curve y equals kx cubed minus 2x squared minus x plus 7 is 3, at the point where x equals 2, find k. Okay, so we have y, so dy dx is given by 3 times kx squared minus 4x minus 1. So dy dx, that's all equal to 3 because we're told the slope is equal to 3, and dy dx is the slope of the curve. So that's all equal to 3. So if we incorporate the 3 here and let all that equal to 0, so 3 minus 3 becomes minus 4, all to 0. Then at x equals 2, we simply sub x equals 2 in, we'll find that k is equal to 1. Now, just a bit of theory on maximum and minimum turning points. So we have a curve that turns at A, that's the maximum turning point, and turns again at B, at the minimum turning point. And the important thing to note is the slope at that point, or slope at this point, dy dx, is equal to 0. The slope is equal to 0, dy dx is equal to 0. So at turning points on a curve, dy dx is always equal to 0. And just to note that quadratic functions only have one turning point, that either a maximum point if a is positive in the equation, or a minimum turning point if a is negative. It's minus 3x squared. If you were to plot that function, you'd end up with a parabola. No, sorry, that's positive, and when a is negative. So that's when a is positive. So 3x squared would give us something like this, 3x squared plus blah, 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 and minus 3x squared would give us a plot like that. Okay, so a is positive, we get a minimum turning point, and a is negative, we get a maximum turning point. Okay. So by example, okay. Find the coordinates of local maximum and minimum turning points on the curve y equals x cubed minus 9 squared plus 15x plus 2. First thing, find dy dx. That's equal to 3x squared minus 2 nines or 18x plus 15. Okay, and when dy dx equals 0, well actually before we, when dy equals 0, we'll let all of that equal to 0, but we can simplify this equation here by just dividing every term by 3. So we'll have x squared minus 6x plus 5 equals 0. And we'll find the factors of that expression, x minus 5 and x minus 1. So x is equal to 5 or x is equal to 1 because we let them equal to 0 here. Okay. So then when we let x equal 5, we sub that value of 5 into where we see x, and we get y equals minus 23. So that's either a max or a min turning point. And we let x equal 1 and sub that in, and we get y equals 9. And that's the other max or min turning point. How do we know which is which? Well, this must be the max turning point before we hit the min, because the 9 is higher up on the y scale than the minus 23. Okay, so it must be, this is the max, and this one then must be the minimum turning point. Now let's consider second derivative. So we can actually we can differentiate again if you like. We have a function we can find dy dx, but we can also find d2y dx squared. Okay, so we're going to talk about the second derivative, this d2y dx squared, and the nature of turning points with respect to them being positively rising or negatively decreasing. Positively rising, there it's negatively decreasing, there it's positively rising, or the slopes at any of these points are positive. The slopes at any of these points are negative, and they're positive again. Okay, so at a maximum turning points, dy dx equals 0, and d2y dx squared is less than 0, it's negative. And at a minimum turning point, dy dx equals 0, and d2y dx squared is greater than 0, i.e. it's positive. Okay, so for the last example that we looked at, we had a turning point at 1, 9 and 5 minus 23. And our dy dx was x squared minus 6x plus 5. So our d2y dx squared is simply 2 by x minus 6. So we're just we're differentiating that to this. And so at x equals 1, we can see that at x equals 1, this d2y dx squared, what's that equal to? Well, it's equal to minus 4. It's negative. So that proves that it's a maximum turning point from this rule up here. And if we let 5 into our d2y dx squared, we get a positive value of 4, and that tells us that that's a minimum turning point. So it's another way of finding the max and min turning points by differentiating a second time.